In the last few videos, we looked at topics pertaining to aldehydes and ketones, where we started by defining aldehyde and ketone functional groups. We talked about nomenclature of these classes of molecules, and then we talked about physical properties of these compounds. In this video, we are going to focus on one of the key reaction types of aldehydes, that is, oxidation reactions. Oxidation reactions of aldehydes are critical to biology and medicine, hence why we have this splash of different molecules and instruments relative to biology and medicine. Let's go ahead and get started with looking at oxidation reactions of aldehydes, which happen physiologically within the body using enzymes as the catalysts for these reactions. In this video, we will look at both enzymes as the catalyst for oxidation reactions of aldehydes, as well as how these types of reactions would be carried out in a lab. So focusing on oxidation of aldehydes, the first thing that we will do is a reminder of what we are dealing with when we talk about the term oxidation. Oxidation refers, for our purposes, to reactions where we are increasing the number of bonds between carbon and an electronegative atom, such as oxygen, and in turn, we are decreasing the number of carbon-hydrogen bonds because the carbon always has to maintain its complete octet. And if we're raising the number of carbon-oxygen bonds, something has to give, and that something that gives is we lower the number of carbon-hydrogen bonds. And so as we look at an aldehyde molecule, particularly at the aldehyde functional group itself, we have a carbonyl group directly bonded to a hydrogen atom. And then I will go ahead and plug in R here, which could represent any carbon chain, or it could just represent a hydrogen atom here if this was formaldehyde, a one-carbon aldehyde. In an oxidation reaction of an aldehyde, which I will abbreviate O here to represent an oxidizing agent, what will happen is that the carbon-hydrogen bond at the carbonyl right here will be replaced with a new carbon-oxygen bond, hence giving this reaction the classification of an oxidation process. When we replace the hydrogen that's directly bonded to the carbonyl with an oxygen atom, what ultimately results is a carboxylic acid functional group. The R group over here is still the same as it was to start with. So in total, what we've done in this reaction is converted the aldehyde functional group that we started with into a carboxylic acid reaction product. And this is going to be the general paradigm of oxidation of aldehydes. The oxidation of an aldehyde in general is going to lead to a carboxylic acid product. And with this being a general rule here that the oxidation of an aldehyde leads to a carboxylic acid product, we can keep that in mind whenever we're thinking of aldehyde reactions that involve oxidation, is that the expected product will correspond to replacing the carbon-hydrogen bond of an aldehyde with a carboxylic acid group by bringing in this OH hydroxy group into the molecule. Now, what if instead we were focusing on ketone oxidation? Because throughout this unit, we've covered aldehydes and ketones within the same types of terms and talked about some of their analogous physical properties. So what if here we had a ketone where R here would have to equal a carbon atom, making this fit the ketone functional group. And we treated the ketone with an oxidizing agent, which I abbreviate as O. In this case of a ketone, what we will notice is that in the ketone molecule, there are no direct bonds between the carbonyl carbon and hydrogen. The implication of this is when we think about what's happening during these oxidation reactions where we're increasing the number of carbon-oxygen bonds and decreasing the number of carbon-hydrogen bonds, since there are no carbon-hydrogen bonds here at the carbonyl, the group that would be oxidizing, what will be able to happen here is really nothing. Since there's no carbon-hydrogen bonds, there's no point here that can be oxidized, meaning there's no point on this carbon that can be replaced with an oxygen atom. The reason is that these carbon-carbon bonds on the ketone are very, very stable and strong, and hence the oxidizing agent can't break those to insert an oxygen atom in its place. So, since there's no carbon-hydrogen bonds here on the carbonyl group, when you attempt to oxidize a ketone, what ultimately results is pretty boring. It is no reaction. So while aldehydes are extremely susceptible to oxidation because they have this carbon-hydrogen bond that readily breaks and is replaced with the hydroxy group here, ketones are very, very resistant to oxidation, generally undergoing no reaction when treated with an oxidizing agent because of the fact that they have no carbon-hydrogen bond here, and so this carbon of the carbonyl is not suitable for oxidation. Now we can ask the question, since we know that aldehydes are readily oxidized, what sort of oxidizing agents are appropriate? In other words, what types of reagents would we treat an aldehyde with in order to yield a carboxylic acid product? There are a variety of choices here because aldehydes are very easily oxidized, and so generally with aldehydes, they don't require a very strong oxidizing agent to convert the aldehyde group into a carboxylic acid group. So of the oxidizing agents that are available, the ones that are most common that you should be familiar with are oxidizing agents that feature chromium in the 6+ state. So I'll put chromium there and then Vi to indicate 6. Some examples of chromium 6 include K2Cr2O7, where if I was given this in a reaction, I see the chromium there, and that's going to be your telltale sign that you're looking at an oxidizing agent. Generally, this oxidizing agent is provided with sulfuric acid. So if you see H2SO4 there in your reaction, don't be alarmed by what that means. It's required as a component of this oxidizing agent mixture. Oxidation of aldehydes can also be accomplished using bleach. And that's one reason why bleach is a common agent for disinfecting, because bleach, due to the fact that it oxidizes a wide variety of molecules, including alcohols, as we talked about in an earlier unit, by oxidizing a variety of biological molecules, it causes death of the microorganisms that it comes into contact with, hence making bleach a strong disinfectant. Additionally, a substance known as potassium permanganate is another example of an oxidizing agent. And although I'm writing it out in words here, you will typically instead see its formula KMNO4. And potassium permanganate is a pretty interesting example of an oxidizing agent because it has a bright purple color. So with potassium permanganate, if you are using it, you will notice that what you're mixing into your reaction is generally this kind of pink or even a darker purple color that you will notice depending upon how concentrated or unconcentrated this is. Each of these are ways that we would go about oxidizing molecules in a laboratory, or in the case of bleach, generally we don't typically use that in a lab, but instead we use it as a disinfectant due to its strong oxidizing properties. In biological systems, enzymes are what carry out the work of catalyzing chemical reactions. When we say that something catalyzes a chemical reaction, it means it makes the reaction tremendously, tremendously more favorable by speeding up the rate of the reaction. We'll get more into how that works when we get into our chapters on proteins later on. But for now, I want to make you aware that the type of enzyme that oxidizes aldehydes is called an oxidase. There are a variety of different oxidase enzymes, depending upon exactly what organism you're looking at and what type of molecule it oxidizes. The way that we can recognize this as an enzyme is enzymes end in this suffix ase. So our telltale sign here that this is an enzyme and not a standard chemical reagent such as the ones that we've talked about up top here is that ase ending. So oxidases, as the name kind of implies, oxid, is referring to the fact that this enzyme catalyzes oxidation reactions. And so within the human body, for example, if one consumes ethanol, ethanol becomes oxidized via an oxidase to acetaldehyde, a 2-carbon aldehyde molecule. So the reaction goes like follows. We have alcohol, ethanol, becoming oxidized via an oxidase enzyme to a 2-carbon aldehyde, and then that 2-carbon aldehyde is recognized by an oxidase enzyme that catalyzes the conversion of that into a carboxylic acid functional group. So as we are thinking about aldehydes, when working with reactions of aldehydes, you may be faced with a reaction where you see an aldehyde reactant and then any one of these oxidizing agent types listed here. You may also alternatively simply see listed above the reaction arrow an O in brackets, indicating that we're using some oxidizing agent, which could be any one of these. So if you look above a reaction arrow and you see this O in brackets, that's your telltale sign that oxidation is what's going on, and you need to convert the aldehyde functional group into a carboxylic acid functional group, as we've done here in this example problem below. So let's now try our hand at an example problem that applies the concepts we've just looked at. I strongly encourage you to hit the pause button here, try to take a look at this problem on your own, see how it goes, and then hit play to determine whether you've reached the correct answer or not. We start here in this problem with 3-oxohexanal. Hexanal will be a 6-carbon aldehyde. So I'm going to go ahead and draw in my 6-carbon aldehyde. Drawing this as a line angle formula, since it doesn't specify what type of structure we are required to draw here, you can show it as whatever you want. So we have our 6 carbons, and I need to add 1 more carbon to get up to 6 there. So we have 1, 2, 3, 4, 5, 6. And at position number 3, we have an oxo group. We previously, when talking about nomenclature, described an oxo group as a carbonyl group, where we're referring here to a ketone branch. So at carbon number 3, 1, 2, 3, because we number from the aldehyde group, we have a carbonyl branch coming off. So this is our structure, 3-oxohexanal. And what we're saying when we describe this as the 3-oxohexanal was treated with potassium permanganate, KMnO4, is that we're mixing the starting organic molecule, that is our 3-oxohexanal, with potassium permanganate, KMnO4, and then predict the structure of the major organic product. So we need to draw in what would result here as our final major organic product, where we're saying, what is the organic substance that would result from mixing these two together? What's our reaction product, in other words? So looking at our structure and evaluating it, we've recognized here, if we are tackling this problem, immediately drawn to our attention is that our potassium permanganate is an oxidizing agent. We could abbreviate that as O in brackets. We recognize that an oxidizing agent carries out the conversion of carbon hydrogen bonds to carbon oxygen bonds to oxidize the reactive locations of the molecule. Within the molecule, our carbonyl groups are the possible sites of oxidation, but only if the carbonyl group has a hydrogen directly bonded to it that we can replace with an oxygen atom. So looking at our structure, we have both an aldehyde group and a ketone group. At our aldehyde group, we have our carbon-hydrogen bond. What we will do here is to oxidize that, we will replace the carbon-hydrogen bond with a carbon-oxygen bond. And fill the complete octet, that will actually become a COH bond there. On the other hand, at position number 3, where we have our oxo group, you will notice that on both sides of that carbonyl group, here's our carbonyl, we have a carbon here and a carbon here. There's no hydrogens directly bonded at position 3, and therefore there can be no oxidation possible. In other words, that particular location of the structure is unreactive. Therefore, when we draw in our product here, we will oxidize that left terminal end of the molecule by replacing the hydrogen that's bonded there with a hydroxy group to make a carboxylic acid functional group product there. And then coming down the chain, we still have our 6 carbons in total. At position 3, we will still have our carbonyl group of a ketone, since that group, that carbonyl, can't be oxidized since there is no hydrogen directly bonded to the carbonyl carbon. So our final product of this reaction, and what you would need to draw in order to be correct on this problem, is what I've shown right here. And since the problem doesn't ask you for a particular type of drawing, such as a line angle formula that we showed here, since it just says predict the structure, you could show that as a Lewis structure, a condensed structural formula, line angle formula. Really any of those acceptable ways of drawing a molecule would be perfectly acceptable there, since it doesn't specify what type of drawing is required. Now, in the next video, as we move on, rather than focusing on oxidation reactions where we're increasing the number of bonds between carbon and oxygen, instead we'll focus on the reverse reaction, which is referred to as a reduction reaction, where we are decreasing the number of bonds between carbon and our electronegative atom, oxygen, and increasing the number of bonds between carbon and hydrogen. Let's go ahead to that video.